Motion from electricity. The voltaic pile provided scientists a steady, reliable source of electricity for experimentation. It would take another 20 years before scientists realized its possibilities. Hans Christian of Copenhagen observed that when a current-carrying conductor was placed near a magnetic compass, the compass needle deflected. He also observed that if current flowed in the conductor was reversed, the compass needle deflected in the opposite direction. Ørsted's observations were summarized into two widely accepted conclusions that laid the foundation for electric motor. A conductor that was carrying an electric current emitted a magnetic field that surrounded it. This was observed when the magnetic needle was either attracted or repelled to the current-carrying conductor. This proved that electricity could be converted into magnetism. The magnetic field that was created when electricity flowed in a conductor also interacted with the magnetic field of the compass. This interaction caused the compass needle to deflect, creating motion. This proved that electricity could be converted into mechanical motion. Around the same time, André-Marie Ampere, a French scientific investigator, also duplicated Ørsted's work and formulated his own mathematical relationships. He developed the science of electrodynamics. Using a compass, his observations demonstrated that when an electric current flowed in a conductor, that the strength of its magnetic field increases with an increase in electric current, while decreasing further away from the conductor. He observed that if two current-carrying conductors were sitting near each other, each had an influence on one another. If the electric current flowed in the same direction, at the same time, the two conductors attracted each other. If the current was reversed, in one of the conductors, the two conductors repelled each other. Ampere's achievements in this new science was rewarded by the scientific community when the unit of current was referred to as ampere, or commonly known as amps. An ampere of electric current constitutes 1 coulomb of electric charge transferred in 1 second. Ampere concluded that the magnitude of a magnetic field surrounding a current-carrying single-wire conductor varies with the magnitude of the current flowing in it and inversely with the distance from the conductor. A method was devised to predetermine the direction of the magnetic flux around a current-carrying conductor. This became Ampere's rule for a straight conductor. The rule states, using your left hand grasp the conductor, with the thumb pointing in the direction of the electron current flow. The fingers will now encircle the conductor, in the direction of the magnetic flux. This rule is also referred to as the left-hand rule for a single conductor. He set forth a mathematical relationship between the voltage, the current and the resistance in the conductors. He stated with a constant temperature, the electric current flowing through various conductors is proportional to the potential difference across it. It is written as I equal voltage divided by its resistance. This became known as Ohm's law. Its derivates E equals I, current times R, resistance, or resistance, R equals E, voltage divided by I, current, became universally accepted and became the building blocks for electric circuit design. The name given to the unit associated with resistance is called the ohm and is designated by the Greek letter omega. A resistor is an electric device that is used to control electric current or to produce heat. One of the most common types that we used every day is the wire-wound resistor. Wire-wound resistors come in many variations. One of the most common materials used to manufacture resistors are metals and its different alloys. The most common resistor is the incandescent bulb, in which the filament or resistor is made from fine tungsten wire. The resistor elements of electric toasters, heaters, and irons use nickel-chromium wire in wire or ribbon form. The wire-wound resistor is basically a resistance wire wound in a continuous coil around an insulated form. Some of the common types are pictured below. The picture to the right shows a few of many different types of potentiometers in use today. A potentiometer is similar to a rheostat having a movable slider, mounted on a shaft, that when rotated selects different resistances and sends its variations to its output lug. A rheostat, showing the front knob, that is set screwed to a through shaft, on which a contact brush and slider assembly is mounted. The insulated coil is wound on an insulated form so that the turns are sitting side by side. This is called a layer winding. As the front knob is turned, the shaft and slider assembly rotate the contact brush across the flat surface of the wound series turns. The area of coil that the brush is riding on is cleaned of all insulation, ensuring that there is no turn-to-turn shorts. Some rheostats are wound using uninsulated wire, again in the winding process, ensuring that there is no turn-to-turn shorts. Composition resistors are molded rods made from a mixture of finely and powdered electrically material. One of the most common types of material used is graphite, with an inert binder. The binder forms a consistency, which holds the mixture together. Copper wire leads are affixed axially in each end of the conductive mixture. For insulating purposes, the complete assembly is remolded within a bakelite case. In 1821, Michael Faraday, a British scientist, developed the first electric motor. It was a single apparatus to demonstrate that electricity could produce a continuous mechanical rotation. Although Faraday's apparatus could not be used for any practical application, it did however unlock the door to the future for the invention of the electric motor. Faraday's electromagnetic rotary apparatus consisted of a straight platinum wire suspended from a metal support, which allowed it to rotate about it freely. The other end of the wire was suspended in a dish that contained a pool of mercury. Mercury is a liquid at room temperature and, since being a metal, is a conductor of electricity. A circular magnet was affixed at the center of the dish of mercury. Two electrodes made contact with the apparatus. One electrode made contact with the apparatus. One electrode made contact with the mercury pool and the other with suspended platinum wires. A voltaic cell was connected to these two electrodes. When the voltaic cell was connected, electricity flowed through the platinum wire. The electricity flowed through platinum wire, through the mercury, returning to the cell. This electric current flowing through the platinum wire created a magnetic field around it. This magnetic field interacted with the magnetic field of the magnet and the wires began to rotate around it. Faraday demonstrated that electricity could produce continuous mechanical motion in a rotary shaft. The Faraday electric motor is shown. Faraday observations and experiments led him to discover what is referred to as electromagnetic induction. He observed that if a moving magnetic field was introduced close to a nearby electric conductor, that the conductor had an electromotive force produced in it that caused an electric current to flow in it. A permanent magnet that had a handle attached was inserted into the center of a wound copper coil. It was observed that when this magnet was thrust in and out of the coil, an electric current was induced in the conductor. This electric current was called an electromotive force. Faraday proposed the idea that invisible magnetic lines of force were actually cutting through the individual turns of the copper coil conductor, causing an electric current to flow through it, as indicated by the galvanometer. If the magnet came to rest, there was no electric current flow. Faraday referred to this phenomenon as an induced electromotive force, caused by electromagnetic induction. He also devised an induction ring where two separate insulated copper coils were wound about each other on the iron ring. The individual coil was tapped into various locations, bringing out external leads, which were connected to a voltaic cell. By applying electric current to one of the copper coils, an electromagnetic field was created. This caused expanding invisible magnetic lines of force to cut through the turns of the second coil, inducing an electromotive force into it. When a steady state is reached, the current in the second coil ceases. When the first coil is disconnected from the battery, another instantaneously current flowed in the second coil again, but flowed in the opposite direction. This current was referred to as alternating current, since it constantly reversed. This again was electromagnetic induction, and the ring was an early form of the transformer. Learn electric motor inspection and testing techniques. Introducing a new edition of electric motor inspection and testing, Nickel Handbook, which covers motors from 1/4 horsepower to over 5,000. Topics covers the inspecting and testing of the insulation system, checking the continuity and measuring the resistances of the windings. It recommends the acceptable allowable readings and values associated with test results. Surge testing and high potting, both AC and DC windings. Also give tips and techniques of how to test run AC motors, outlining what the no-load amperes, the temperature limits of the bearing. The motors can range in horsepower from hundreds to thousands, including synchronous, vertical, and other specially designed motors. Servo motors and encoders, resolvers, and tachometers. Commutators and commutation issues, including slip rings, and permanent magnet direct current motors. Medium and large size direct current motors, with field coils, and armatures are clearly covered within the material. Core loss testing of both AC rotors and DC armatures are also discussed. Performing a core loss test on AC motor cores. Various types of AC rotors are also discussed within the material covered. Textbook number 1, Inspection and Testing of AC and DC Electric Motors. 223 pages of inspection and testing procedures, used in most repair shops today, plus tips and techniques information sheets. Textbook number 2, AC Electric Motor Repair, 230 pages of electric motor repair procedures and techniques, plus tips and techniques, information sheets. Textbook number 3, DC Electric Motor Repair, 215 pages of DC electric motor repair procedures and techniques, plus tips and techniques information sheets. Textbook number 4, Armature Winding and Repair, 206 pages of mush coil and form coil, armature winding and repair procedures, plus tips and techniques information sheets. Textbook number 5, AC 3-phase electric motor winding procedures. The book has 228 pages of technical procedures for rewinding random and form coil motors. It also includes tips and techniques associated with winding, testing of mush and form coil rotors. The books are also available in PDF format, on DVD. The series also has 2 different DVDs titled Electric Motor Repair Disc 1. It covers both AC and DC motors. The second DVD, Electric Motor Repair Disc 2. It covers overhauling large DC motors. The books and DVDs can be purchased online through Amazon.ca. For more information, go to our website at twmmediaservices.com or email us at twmenterprises@rogers.com.